Welcome to this lecture on fundamental of electric drives. In the last lecture, we were discussing about fully controlled rectifier fed separately excited DC motor, and what we saw was that we can divide the operation into two categories. One is a continuous current operation, other is a discontinuous current operation. So, we started in the last lecture with the discontinuous current operation. So, let us resume from where we stopped in the last lecture. Now, this is the discontinuous armature current operation, where we have the armature current which is discontinuous, which means which is rising and then coming down to 0 and then starting from 0 again coming down to 0. So, the current is touching 0 in every half cycle. Now, we have to analyze this circuit with mathematical equation. Now, if we see that the converter here, this is the single phase converter and this is the load, and the load is a DC motor. Now, the DC motor is represented by the armature resistance, the armature inductance and the back EMF. Now, during this discontinuous current operation, what we do here, we trigger the SCRs T1 and T2 in the positive half cycle. So, here is the triggering of this SCR in the positive half cycle. So, the thyristor T1 and T2 are triggered in the positive half cycle, and the current starts from 0 and it gradually builds up, and then again it comes down to 0 at an angle that is beta. So, this angle is beta, the extinction angle. So, and then afterwards the current is 0 till the next pair of SCRs are triggered. The next SCRs are T3 and T4. So, these SCRs are triggered in the negative half cycle. So, this is the instant at which we trigger the next two SCRs, that is T3 and T4, and the voltage across it reverses. So, we get the output voltage which looks like this, and we can divide this output voltage or the operation of this converter into few modes, two modes at least. One is called the powering interval, that is from alpha less than omega t less than beta, from alpha till beta, this is called the powering interval, and from beta to pi plus alpha up to the instant when the next SCRs are triggered, this is called the coasting interval or zero current interval. Zero current, at this instant we do not have any current. So, we can call this as zero current interval. In the first zone, first interval, which is called the powering interval, we can see that the applied voltage, that is Vs, this is the source voltage. We trigger these two SCRs T1 and T2. So, the conduction is through T1 and then the load back to the source through T2, and in that case the armature voltage is same as the source voltage, and the current starts from 0 and then it builds up, and then when the voltage becomes negative, even after omega t equal to pi, it still conducts, but the current decreases because the supply voltage here is negative. So, the current becomes equal to 0 at omega t equal to beta, and this interval stops when omega t is equal to beta. And then afterwards we have from omega t from beta to pi plus alpha, we have the 0 current interval. When the current is 0 here, there is no current flowing in this case. So, the back EMF here, the supply voltage or VA, the armature voltage is same as the back EMF. So, that is seen by this part of the curve or this part of the region where the supply voltage is same as VA is same as the back EMF. So, that is called the zero current interval. So, let us analyze these two interval separately. Now, in the powering interval we saw that this is the region omega t between alpha and beta. So, VA is equal to Vs. So, we have a first order differential equation. The armature voltage is same as the AC input voltage, and that is equal to R A L A d I A by dt plus E is the back EMF, and the input here is Vm sin omega t, and that is equal to the resistance drop R A I A, the inductance drop L A d I by dt plus the back EMF which is E. Now, this is a first order differential equation, and we have to solve this first order differential equation. Now, this equation, the solution of this differential equation consists of two parts. One is a steady state component, other is a transient component. So, the solution of this equation has got a steady state component and also has a transient component, and the steady state component has got these two terms Vm by Z sin omega t minus theta, because we have a circuit which is which has a armature resistance, inductance and a back EMF, the resistance, the inductance and back EMF. So, when we write this equation for an RLE, this is a RLE circuit and this is the applied voltage, that is VA, which is same as Vs here. So, the steady state component, the current which flows here is IA, is having two components. One is because of the input voltage VA, which is AC voltage, and the other one we have another source here, that is E, the back EMF. The back EMF is trying to oppose the current, because this is trying to drive a current in the opposite direction. So, we have the AC steady state current is Vm by Z sin of omega t minus theta, and the DC current is opposing this current IA, which is minus E by R A. So, this is a steady state component, and we also have a transient component. The transient component is A exponential minus t by tau A, where tau A is the time constant of the circuit. Now, why does a transient component come into play? Because here the triggering angle is changing. We can change the triggering angle. The alpha is variable here. If we see in this case, we can change the triggering angle. The alpha is variable, but when we trigger the SCRs, the current has to start from 0 to satisfy the boundary condition, that is a transient component. So, we have to calculate what is this constant A. Now, this equation we can say that at t equal to omega t equal to alpha, the current IA has to be equal to 0. So, we substitute this, let us say we call this to be equation number 1, we substitute this in equation number 1. So, what we get here is 0 is equal to Vm by Z sin, and omega t is alpha here, alpha minus theta minus E by R A plus exponential E. So, what we do here, we multiply here omega, and omega t is now alpha. So, in this case we call this to be alpha by omega tau A. Now, omega tau A is equal to omega L A by R A, this is equal to tan theta. we have defined the tan theta previously. So, omega L A by R A is tan theta, or R A by omega L A is called cot theta. Inverse of tan is cot, 1 upon tan is cot theta. So, since this is 1 by omega tau A, we can rewrite this as V m by z sin alpha minus theta minus E by R A plus A exponential minus alpha into cot theta. Now, we have to find what is the value of A. The value of A here is equal to E by R A minus V m by z sin alpha minus theta exponential alpha into cot theta. This has been obtained from the previous equation. So, we are trying to find out what is the value of this constant A, so that we can substitute this here to get the value of current, that is I A. So, this value of constant can be obtained from this equation. From this equation we get the value of the constant, which is A. Now, we go back and substitute this value in the equation number 1. So, what is I A? I A is V m by z sin omega t minus theta minus E by R A plus A is here. So, we have E by R A minus V m by z sin alpha minus theta exponential minus omega t minus alpha cot theta. So, we have substituted this value of A in this equation, equation number 1. So, in this equation when you substitute this value of A, we get this equation. So, this equation is the equation of current for omega t greater than alpha less than beta. You can say greater or equal to alpha, also does not matter, less equal to alpha. So, this is the value of I A. Now, what we have to do is that we have to find out the value of I when omega t is equal to beta. So, we can say that at omega t equal to beta, what is the value of I? I becomes equal to 0. And what is beta here? Beta is called the extinction angle. Extinction angle of the converter. So, at omega t equal to beta, current again comes down to 0, because we have negative voltage, current comes down to 0 at omega t equal to beta. So, if we substitute this value in the previous equation, this is equation number 2. So, what we get here is 0 is equal to V m by z sin beta minus theta minus E by R A plus E by R A minus V m by z sin alpha minus theta exponential minus beta minus alpha cos theta. So, this is a transcendental equation. This is not a simple algebraic equation, because this contains sine and exponential function. So, we have to evaluate what is beta. So, beta can be evaluated iteratively. So, beta, if you want to find out what is the value of beta here, the extinction angle, this value of beta can be evaluated iteratively. Beta can be evaluated from equation, we can call this equation number 3 iteratively. We take some initial value of beta and then we try to take some value in the neighborhood of the initial value, and by iteration we can come to an approximate value of beta. So, say for example, we can start with beta is equal to pi plus theta. Let us, this is a good initial value, theta is the power factor angle that we already discussed. So, start with the beta is equal to pi plus theta, then calculate or evaluate the final value of beta, so that equation 3 is satisfied. Now, this is how we find out the extinction angle. Now, what is the boundary between the continuous operation and discontinuous operation? Now, if we see here, boundary between continuous and discontinuous operation. So, we can say that beta is equal to pi plus alpha. Now, this is the boundary condition, after that current becomes continuous. Now, let us try to see when this happens. This happens when beta is equal to pi plus alpha. Now, what we do here, we substitute the value of beta in the equation number 3 and try to find out the boundary value. So, substitute the value of beta equal to pi plus alpha in equation 3 and calculate the speed for boundary condition. So, what we do here, we go back, and then what we do here, we substitute the value of beta in this equation number 3 and see under what condition we get this boundary between the continuous and discontinuous operation. So, 0 is equal to V m by z into sine of pi plus alpha minus theta minus E by R A plus E by R A minus V m by z sin alpha minus theta exponential minus omega t, here we have got minus beta here. So, that is minus pi plus alpha into, we can substitute the value here and then get the boundary condition. So, this is beta minus alpha. So, what we are trying to do here, we are substituting beta by pi plus alpha. So, alpha alpha will cancel. So, what we get here, minus pi cot theta. So, exponential minus pi cot theta minus pi cot theta. So, this is the condition for which there is a boundary between the continuous operation and discontinuous operation. Now, from this we can find out the value of the critical speed. So, if you simplify this, we get the value of the critical speed, and this value of the speed is given as R A into V m divided by z k phi sin alpha minus theta into 1 plus exponential minus pi cot theta divided by exponential minus pi cot theta minus 1. This is the value of the critical speed. It means, if the speed is above the critical speed, the operation is discontinuous. If the value of the speed is less than this critical speed, the operation is continuous. So, we can say that if the speed of the motor is above omega m c, the operation is discontinuous. So, if the speed is less than omega m c, the operation is continuous. Now, let us try to draw the torque speed characteristic under discontinuous current operation. Now, if the current is discontinuous, what we observe here is the following. Let me draw the speed torque characteristic, the voltage, the output voltage once again. We are having the back EMF here, which is E, and the triggering at an angle alpha. This is pi, again we are triggering at an angle alpha. So, this is the extinction angle, that is beta. So, the output voltage looks like this. This is the angle beta here. So, this goes of this sort, and this is how the output looks like. This is alpha, pi, this is beta, and then again we have pi plus alpha. Now, what we need to do here, if it is a periodic, we have the waveform which is like this. So, this is the armature voltage V A. Now, what we need to do here, we need to find out the average armature voltage. So, what is the average armature voltage applied to the DC motor? So, if you want to find out the average armature voltage, we integrate for 1/2 cycle. So, the integration is for 1/2 cycle, that is pi. So, we start with alpha. We start with alpha to beta. We have Vm sin omega t d omega t, plus from beta to pi plus alpha, the value of the voltage is here, the back EMF, that is E. So, from beta to pi plus alpha, the value of the voltage is E, and the integration is over d omega t. Now, let us simplify this. This is equal to 1 by pi. Now, this is Vm cos of alpha minus cos beta, plus this is E pi plus alpha minus beta. So, whole over pi. Now, this is our armature voltage. Now, this has to be equal to the resistance drop plus the back EMF. The back EMF is E. So, we have the back EMF in two places. We have a back EMF here, we also have a back EMF in the left hand side. So, we need to evaluate what is the speed torque characteristic here. So, we can take the back EMF to one side. So, E into this we have, this is what we have here, E into 1 minus pi plus alpha minus beta by pi, that is equal to Vm into cos of alpha minus cos of beta by pi minus I A R A I A. Now, from this what we get here E into here we have pi minus alpha plus beta by pi, that is equal to V m cos alpha minus cos beta by pi minus R A I A. So, or we can say that E is equal to V m into cos alpha minus cos beta divided by beta minus alpha minus R A I A by beta minus alpha into pi. Now, this is an equation from which we can get the relationship between the torque and the speed. Now, we have also known in the previous lecture that what is the back EMF? The back EMF is given as k phi omega m. What is the torque? Torque is k phi I A. So, we can substitute for the current I A is T by k phi. So, what we get here is finally from this equation omega m is equal to V m into cos alpha minus cos beta by k phi into beta minus alpha minus R A torque into pi by k phi whole square into beta minus alpha. So, this is the torque speed characteristic of a separately excited DC motor when we have discontinuous operation. Now, let us see what is the torque speed characteristic for continuous operation. In continuous operation, what we have is the following. The current is continuous here. So, we have the voltage, we have the back EMF here, we trigger it at an angle alpha, this is pi and this is pi plus alpha. So, the current here, if we draw the current in this case, current is continuous, current does not come down to 0. So, this is our voltage and the voltage looks like this. We are triggering at an angle alpha and then it is continuous till pi plus alpha. So, the voltage waveform looks like this. This is 2 pi, this is pi and the current waveform is continuous, that is I A, current does not come down to 0. So, this is the continuous current operation where we do not have discontinuity in the current is fully maintained in both the half cycles. So, we do not have to solve this complicated equation. So, the analysis of continuous current operation is simpler than that of a discontinuous current operation. We will try to derive the average voltage equation and the torque speed relationship for the continuous current operation in the next lecture.